Today, we are diving deep into network flow. This is one of those core computer science concepts that, it's kind of the hidden engine behind everything, from how your internet traffic gets routed to how global supply chains are optimized. So let's get right into it. This is really the central question, isn't it? How do you squeeze every last drop of performance out of a system you already have, with all its built-in limits? The answer, as you'll see, is not just clever. It's an elegant, powerful, and mathematically guaranteed optimal solution. So here's the plan. We're going to start with the basic intuition. Then we'll hit that big aha moment with something called residual graphs. After that, we'll look at the mathematical guarantee that tells us we're right, see a real algorithm in action, and finally talk about why any of this is so important in the real world. All right, to really get a gut feeling for what network flow is all about, we're not going to start with a bunch of scary graphs and equations. Nope, we're going to start with something way more familiar, a network of water pipes. Okay, just picture it. You've got a water source, like a lake, and a destination, the sink. Your job is to get as much water there as possible. So you find a path of pipes. You turn on the water, but you can only push as much as the skinniest pipe on that path will allow, right? That's your bottleneck. Then you look for another path that still has some room, and you do it again. And you just keep repeating this process until there's absolutely no way to get one more drop of water from the start to the end. That's the core idea in a nutshell. Now, let's put on our computer science hats and translate that. A flow network is just a directed graph. You have a start node, we'll call it S for source, and an end node, T for sink. And every connection or edge between them has a capacity, a hard limit on what can flow through. The rules are pretty simple. You can never push more through an edge than its capacity, and for any node in the middle, whatever flows in has to flow out. Simple. Okay, so that water pipe analogy is great, but it has a pretty big flaw. What if the first path you picked was actually a really bad choice? What if it stole capacity from a path that would have been way better overall? This is where the real genius of the solution comes in. It's an idea called the residual graph, and it's the key to everything. This is where the magic happens. After we push some flow through a path, the residual graph doesn't just keep track of how much capacity is left. It does something incredible. It creates a reverse edge. This new edge basically represents the flow we just sent, and it gives our algorithm the power to undo a bad decision. It can push flow backward along this reverse edge, effectively freeing up that capacity so it can be rerouted along a better path. It's a game changer. So, with this superpowered residual graph, what are we actually looking for? We're on the hunt for something called an augmenting path. And that's just a fancy way of saying we're looking for any path from the source to the sink that can still carry some flow. If we can find one, it means we haven't maxed out the network yet. We can still push more. This all leads to the really big question, right? How do we know when we've actually found the absolute maximum flow? How can we be 100% sure there isn't some super clever, sneaky combination of paths we've just missed? Well, the answer is one of the most beautiful and elegant theorems in all of computer science. This is it, the max-flow min-cut theorem. It's profound. What it says is that the absolute maximum amount of stuff you can push through a network is exactly equal to the capacity of the narrowest bottleneck that separates the source from the sink. It's this perfect, stunning duality between two seemingly different ideas. So what on earth is a cut? Imagine taking a pair of scissors and cutting the graph in two. You draw a line that separates all the nodes into two groups, one group with the source, S, and another group with the sink, T. The capacity of that cut is just the total capacity of all the pipes that cross your line, going from the source's side to the sink side. The min cut, then, is the cut you could make with the smallest possible total capacity. So here's the crucial takeaway. This theorem gives us a perfect way to know when we're done. When our algorithm finally stops, when it can't find a single augmenting path left in that residual graph, we know with mathematical certainty two things. One, we found the maximum possible flow. And two, that flow's value is equal to the capacity of the network's true bottleneck, the min cut. Okay, theory is awesome, but how do we turn all this into a practical algorithm that we can actually code? The general strategy is called the Ford-Fulkerson method, and we're going to look at a specific and really efficient version of it called Edmonds-Karp. The overall method is pretty much exactly what we've been describing. You start with zero flow. Then, as long as you can find a path from S to T in the residual graph, you find that path's bottleneck, you push that much flow through, and you update the residual graph, making sure to add those all-important reverse edges.
Now, the main difference between various algorithms is how they choose which path to use next.
Edmonds Carp makes a simple but totally brilliant choice. It always picks the shortest available path in terms of the number of edges. And it finds this path using a good old breadth first search, or BFS. This one simple rule is all it takes to guarantee the algorithm runs efficiently. And here's a cool bonus. When the algorithm is all done, you can easily find the min cut. It's just all the nodes you can still reach from the source in that final residual graph.
And that simple choice of using BFS has a massive payoff. The time complexity for Edmonds Carp is big O of V times E squared, where V is the number of nodes and E is the number of edges. Now, it's not the absolute fastest algorithm out there, but this polynomial time guarantee means it's reliable. It's not going to suddenly blow up on you, which makes it a fantastic and practical choice for a ton of problems. And what about memory? Well, the news is good there too. It's really efficient. It basically just needs enough space to store the residual graph and to keep track of the path during its search. This means its memory usage grows in a nice, predictable, linear way with the size of the graph. That's excellent.
Okay, we have waded through all the theory and looked at a real algorithm. But where would you actually use this? Why does it matter? Well, it turns out the applications are incredibly diverse, and they pop up in some really surprising places.
Seriously, it's everywhere. From figuring out the most efficient way to route internet traffic, to matching doctors to hospital shifts, or even for figuring out if your favorite sports team has been mathematically eliminated from the playoffs. MaxFlow is this incredibly powerful tool for modeling any problem that involves optimizing some kind of movement through a system with constraints. Now, while Edmonds Carp is a fantastic, reliable workhorse, it's worth knowing it isn't the only algorithm in town. For specific kinds of problems, like bipartite matching, an algorithm called Dynic can be a lot faster. And for really dense graphs, push-relabel methods are often the champs. But for interviews and general use, Edmonds Carp is your go-to because it's simple to understand and has solid guarantees. So if this topic comes up in a technical interview, here's your cheat sheet. Number 1, you have to explain the undue power of reverse edges in the residual graph. That's the key insight. Number 2, know the complexity. O of V E squared. 3, be ready to explain how to find the min cut from that final graph. And finally, to really impress, mention that you know about faster alternatives like Dynic for special cases. So we've done it. We've mastered how to find the maximum possible flow through any network. But what if every pipe also had a cost? What if sending water through one path was more expensive than another? How would you find the cheapest way to send a specific amount of flow? Well, that, my friends, opens up a whole new world of amazing problems. And that's where we'll leave you to explore. Thanks for joining me.